Here are some practice problems in predicting the products of E2 reactions. So we're going to identify these as E2 and predict the major and minor products. We know they're E2 because we have a strong base, which is also a good nucleophile, but primarily strong bases will lead to E2 reactions preferentially. So once we've established that it's E2, we need to decide where the beta hydrogens are, and there are 2 beta hydrogens on this molecule. There are no beta hydrogens on this carbon, so we don't have to worry about it. And because there are 2 beta hydrogens, and we have free rotation around this CC bond, we can use either beta hydrogen to eliminate in our E2 mechanism. And of course, the E2 mechanism is pretty simple. It's simply a proton transfer, followed immediately, essentially in the same step, by the expulsion of the leaving group, so loss of leaving group. So we have PT and Lg, of course, and one of the products will look like this. This is a trans alkene. And because there are 2 hydrogens, we could use the other hydrogen, and that's going to give us the cis alkene. And essentially we get that because we use, if we envision the Newman projection, so let's see if we can draw that Newman projection here. I'm going to look down this bond, and so my Newman projection will look like this. 2 hydrogens on the bottom left and bottom right, and then the back carbon has a phenyl ring. I'm going to use PH to abbreviate phenyl because it's just easier. And then the bromine is going to be right here, and there's another hydrogen that plays no role. I'm going to call these HA and HB because there are 2 of them that we're going to use. And you can see here that HB is lined up anti-paraplanar to the bromine. And so we can use sort of this arrow push, and it's hard to draw the alkene forming, but you can envision it. It's the same arrows that I drew in green above. And this gets us to a alkene where HA is on the same side of the alkene as the phenyl, and this H, well, let's call that C. This is HC right here. Again, I told you it plays no role, but it's still present. HC is on the same side as the ethyl, and so if we label them right here, I've just created the trans. So the trans forms from minus HB, loss of HB. And if I were to rotate this molecule, let's put HA in the position of HB. So let's rotate it so HA is lined up as the anti-paraplanar hydrogen. And so that's going to put the ethyl down here. HB is up top, and here is HA. Back carbon remains in the same orientation. And of course, all these labels are just arbitrary. I just started labeling hydrogens just to keep track of them. You may have different labels, but it's essentially you should be able to tell which of these different hydrogens would produce the given products here. And so again, if we draw our mechanism, we're going to use the same arrow push again, losing HA, forming the alkene, losing the leaving group. And now we have phenyl and ethyl on the same side, and HB and HC on the same side. And so here I'll draw them in right here. And actually we can be more specific on our original drawing. I can make it so it matches and we can keep track of these hydrogens a little better. Of course, one hydrogen's on a wedge, the other's on a dash, and when I drew it, I had HA right here and HB right here. And you can double check that, but this is simply just a Newman projection drawing. And so now we see that the cis forms from loss of HA. And that's how we know that we're going to get a mixture of products. This is stereoselective, which means we have a mixture of 2 possible stereoisomers. It is not stereospecific, so this is stereoselective. It'll select between 2 possible products, and given the choice between these 2, the major product will be the trans, the more thermodynamically stable product, and this would be the minor product. And can you give me percentages? No, not really. We can't assign percentages to these product distribution unless we actually run the experiment. So perhaps we would tell you or give you some clues, but really all we're asking you is to label major and minor. And that's how we do the analysis. You don't have to use these Newman projections to answer this first question. You just have to be able to understand that we are going to form trans and cis. I use the Newman projections to show you exactly what's happening when we form the trans and the cis, and they come from losses of different hydrogens, minus HA or minus HB. Okay, let's move on to the second problem. And here we have our leaving group. This is again secondary. I'm going to draw in some hydrogens just to keep track of them. We'll call that one HA. This one is HB. The phenyl is just like this ring up here. So there are no H's here. So I only have a couple of choices. And HA, of course, is what we'd call an alpha hydrogen. Let me make that a little more clear. HA is the alpha hydrogen. It is not going to participate in the mechanism. It will show up in the product, though. And so our mechanism is simply our base removing HB, and the carbon-hydrogen bond forming the alkene, and the chlorine getting ejected. Now, because there's only one HB, only one beta hydrogen, I should say that more specific, we know that this is going to be stereospecific. Only one product can form from this arrow push. And now we need to figure out what that is. And oftentimes we need to draw a good Newman projection. So let's look at this, looking down this bond. So here's the front carbon, here's the back carbon. And if I were to do that, I would have a propyl group upwards. I would have HB down and to the right, and then I have my isopropyl down and to the left. And then on the back carbon, I have phenyl projected downwards. I have the chlorine up and to the left, and I have HA right there. HA, of course, it will not participate in the reaction, but we'll see where it shows up in the product. And if I use the same arrow push here to remove HB, form the alkene, and lose chloride, I can observe that the phenyl and the isopropyl should be on the same side, and the propyl and HA should be on the same side of the alkene. And so it's easy for me to draw the product alkene now. I like to start like this. Let's try that again. So I like to start by drawing my alkene just basically straight across. And then I have isopropyl, and on the other carbon I have phenyl on the same side. And then I have HA attached to the carbon that has phenyl, and I have the propyl group. And so is this the E or the Z isomer? Well, on this carbon the phenyl is higher priority, and on this carbon the isopropyl is higher priority, so this is Z. And this is the only isomer formed. Don't draw the E. And there's not really an easy way to predict this unless you draw the Newman projection, or once you get good at visualizing, you can see that HB right here and the chloride are already lined up in sort of the anti-paraplanar fashion. HB is coming towards us out of the page, the Cl is going back, and so you can see already that the isopropyl and the phenyl should be on the same side of that alkene, and indeed they are right here. So with practice, you might be able to take the original drawing and simply predict the product. But oftentimes the question will say, draw me a mechanism and predict the product, and include any necessary drawings within that mechanism to predict the product. And that is essentially saying you better have this Newman projection if you want full credit for this problem. So maybe this problem is worth 10 points. I'll give you 3 points for drawing the correct product. I'll give you 2 points for the Newman projection, and then I'll give you 5 points for showing this 3 arrow push mechanistic step for the E2 mechanism. So you're going to get points for showing this Newman projection. You need to know how to do that, and you may have to review Newman projections in Chapter 4 to do that.